to demonstrate how to set up a function switching method, and then we'll actually run that on the Dart itself this morning. First thing we have to do is set up tune files that have the correct settings in them for each of the functions that we're going to run. So I'm going to pull up a tune file and demonstrate where it is that you change the settings to then use in the function switching method that we'll set up in just a second. So the only thing that changes in these tune files is the orifice 1 voltage. And so we're going to change that here and then save the file, and we're going to save it based on the specific name for the tune file and the specific orifice voltage. We want to make sure that we have all the parameters of the tune correct, and the only thing we're going to change then will be the orifice voltage. So we'll do 20, we'll do 30, we'll save that here, save that, and then we're going to do 60 volts, we'll save that one. And then we'll set one up for 90 volts and save that. Alright, so now we have our tune files set. We can go back to Mass Center Main here, and we can go to the Instrument drop-down menu and choose MS Acquisition Method. Now in here we're going to set up 4 different TOF functions, and each one of them will then have within that function the tune file that will go with it. So we're going to add actually 4 different tune file or TOF acquisition functions, and each one of those will then have a respective tune file to go with it. So the first one we'll choose will be our 20 volt tune to go with the first one. We'll set our start and stop masses, and at the Department of Forensic Science we run from 66 up to 600 for our mass range. And then we're going to set a recording interval at 0.25 seconds, which will allow us to record a spectrum in each function every second. So we'll end up with 4 different functions, 4 different TICs to be able to evaluate the data at 4 different orifice voltages. And here, set each of these parameters. Number 3, we'll choose the 60 volt. And once again, we want each of these functions to be the same except for their orifice voltage. And the last one will be the 90 volt here. 66 and 600, and our recording interval at 0.25. Alright, the next thing we'll do is we'll set in our sequence table. We need to have it run all 4 of the functions. And we have a stop time here of 30 minutes, which would be an overall stop time, but we can stop the functions from collecting data during our acquisition whenever we're finished collecting as much data as we need for that particular file. So that's all we need to do there. We've now set up our function switching method. We're going to save that, and we'll call that this file name, and then we'll exit here, and now we'll go back to the Dart tune screen, which is where we'll run our system from. But first thing we want to do is make sure we have our Dart on and operating. We can set the Dart gas temperature at the Department of Forensic Science. We use 275 degrees for our methods, and we use 4 liters a minute for the helium. So we'll wait for that to warm up, get stabilized in temperature, our discharge voltage, our electrode, and the grid electrode are 150 and 250. That looks fine. Voltage at 3500, so we're good with that. So you can see that we're starting to get spectra produced by the DART. So we'll go in here and set up an acquisition file, and we'll actually run a sample using all 4 of the functions that we just set up. So we'll call this one drug, and maybe just a simple 1. And today's date will be the acquisition folder, so we know where it goes. We're going to choose next. And this is important. We're going to choose use existing MS acquisition method. And we want to make sure that the method that we choose is the one that's in this box here. We can choose that by the down arrow or browsing where those are stored and choose the correct one, which we've already got. Well, we're going to choose this one and open that. And then we can, we don't need to go through any more of these screens, so we can go to Finish. And that will bring up our spectrum viewer and chromatogram viewer, and we will then be able to run the sample as soon as the Start Run button comes up. Now the first thing we'll run is some polyethylene glycol 600 in order to calibrate our mass axis. Can we cut right here, guys, for just a second? All right. Sorry about that. Should put this label on better. Okay. All right, we ready? All right. All right, Start Run has come up, and we can now start the instrument acquiring data, and we'll then run our samples on the DART as soon as we get spectra coming up. There we go. All right. So the first thing we'll run is some PEG 600. For our calibration. Okay. All right, the next thing we'll run is some cocaine. We'll use this as a lock mass. And we'll run this on a glass capillary tube. Once again, we'll just put it in the DART gas stream. Okay. All right. All right. Then the next thing we'll run will be our sample. And this is a methanolic solution of a drug unknown. Okay. Make sure I got something. All right. This will be a methanolic solution of a drug unknown. We'll dip a capillary tube into that and hold it in the gas stream, and we'll see our spectrum appear. And I had a top. There's the top. Lost the septum for that. All right. Alright, we'll stop our acquisition here, and we can turn our dart to standby so we don't waste our helium. Alright, now Chip showed you before the use of the Schrader software to reduce the data. I'm going to show you the Mass Center software. And what we'll do first is open the data file in the chromatogram viewer, and then we'll process our data using the spectrum viewer. So we'll find our drug number 1 here file, and we'll open that. And it says the data is unjust. And that's real trouble. This is stopped. Bear with me just a moment. All right. We're going to have to stop for a second, gentlemen. All right, we're going to pick this up right where we left off at closing the data file, and then we're going to open it in the chromatogram viewer and process the data. All right, so here we are in chromatogram viewer. We're going to take the file, drug 1 that we created, and we're going to open that. And once again, I'm going to show you how to reduce this data using Mass Center as opposed to the Schrader software that Chip showed you earlier. Now, just to demonstrate that there are in fact 4 functions that were collected when we open this data file, we can see TIC1, TIC2, TIC3, and TIC4. These are the 4 chromatograms that are represented by the data that was collected in each of the functions. Now normally we would use the 30-volt function to do all of our processing, but I can see that there's maybe some issues with the peaks that are in there, so I think we'll go to the 20-volt function to do our processing. So the first thing we will do is take our polyethylene glycol peak, and we'll get a spectrum up. And that's not necessarily the one we want. We'll take another one here. Now we're doing an averaged subtracted spectrum, and it looks essentially like that. The next thing we'll do is we'll centroid that data, go from the profile mode to the histogram, and we'll take the settings that we have here and then close that. And then we'll need to use that information to change the mass calibration, and this way we will have the mass axis move to where it needs to be, to our reference of polyethylene glycol. So we have a curve that looks like this. This is our spectrum at the top. This is our reference spectra here of each of the peg peaks. And then this is the difference between those two, showing the curve and where each of the points lie with respect to the curve. Now there's a couple of data points that are a little bit off the curve, and especially this one here. That one being an outlier, we can actually zoom in on that and remove it from our data and improve our curve just a little bit, get a little bit better mass assignments on there. So we're going to remove that one, and you'll see the curve fits much better, our residuals are much better, and our error is less than 1 millimass unit across our mass range from about 100 out to 600. So we'll save that, we'll file, save as, and I like to call that temp peg. We'll save that, and then we'll go back and we will need to close that window, and we'll close that window again. Thank you. Ah, dear. If I can just exit out of there. Alright, looks like we've got that little change made. We'll change this to temp peg so that we can apply that calibration to our function. Now we have just applied that to our 20 volt function, and we've applied that now to any spectra that are opened in that particular function. Now we'll need to go through and as I said, the 30 volt function doesn't seem to have collected data correctly, so we'll need to pull up a spectrum in the 60 volt and the 90 volt spectrum. There may have been an issue with the parameters in the method file when I set that up. So this will be our 60 volt function, and we'll need to apply our centroiding to that, and then we'll need to apply our calibration. And we'll change and change, temp peg, and open that, change again here, apply it to the function, temp peg, and OK there. And then we'll go to our 90 volt function, and we'll change that here. Alright, centroid our spectrum, apply those values, close that, and then change our calibration. Alright, so we're going to slide back up to our TIC1, which will give us, we're going to pull up a spectrum of cocaine, and I'll demonstrate how to lock the drift compensation to a cocaine spectrum. Now what I don't have is the mixture of cocaine, methamphetamine, and nifazodone that we use as our check standards to be able to show that the mass axis is in fact calibrated across the entire mass range. Get a good spectrum up here of the cocaine peak. There we go. Alright, so now we need to centroid this data. And that will give us our histogram spectrum. And what we're looking for is the cocaine peak to be at 304.1549, which it is in fact pretty darn close at the moment. But just to demonstrate what would happen if we actually did the lock mass on this, we'll go into change mass calibration once again, and where it says mass drift compensation, we'll go there and change that, and we'll use the internal mass drift compensation menu. And in here we'll have chosen mass per charge as our reference point, and we have that at 304.1549. And we'll finish that, and it will come up with another calibration curve that will show us how far the sample spectrum here, or the standard as we know it, is to the reference in here. And this obviously was pretty close to start with, but we'll save that as our temp drift file. And we'll replace that because it's just a temporary file. We'll exit, then return. And then this would also be applied to each of the functions as we would collect the data, or as we would reduce the data. So now here we are at the 20 volt function, and we're going to take one of the sample peaks that we ran of the drug unknown, and we'll take the averaged background subtracted spectrum of that, and this is what it looks like here. We've already applied all of our calibrations to that. We merely need to centroid this data, and we'll have all of our calibrations applied. And then we'll need to save the data into a data file, and we'll go File, Save As, and we'll use the Joel DX, the text delimited file, and we'll need to put that in the correct place here. And we're going to call that 081408. And we'll open that and we'll put this in. And this is unknown 4, and we want to label that with some indication of the voltage that we use. In this case, we'll label that with a 20, and that will indicate that it was the 20 volt, or yes, the 20 volt spectrum. So we'll save that. Let's slide down to the 60 volt spectrum, and we'll save a spectrum here also. We'll pull that up, and we'll be able to search this then in the search from list program, this spectrum against spectra that are already saved there. So we'll centroid the peak. We've applied our peg calibration. We haven't applied our lock mass to this one. We can go ahead and do that just to show you. It's change again, and we choose the temp drift. And here we change again, and we choose that file. And this will be the file that we have. We'll want to save that. File, Save As, Joel DX. And this will be our 60 volt spectrum. And we'll stop at that for now, and we'll go over to search from list and see how we did. So here we'll need to open up we've got to navigate to where we have that. Here we are. And that apparently wasn't where we put it. It's a project. It's looking for Joel. It's looking for Schrader files. Well, all right. Not there. Here we go again, gentlemen. I screwed it up again. Workshop 08, Current Mass Center project. Sorry for the delay here. This will be edited out, I'm sure. Workshop 08. Alright, I'm just going to go back and look again. We can edit this out. Joel DX folder. Center data. All right, we're going to pick up here from where we left off. We're going to open the file in search from list, and we'll start from here. So we'll roll from here. All right, so we need to navigate to our saved data and make sure we're looking for the correct type of data here, the Joule DX. And here's our 20-volt spectrum. Now we'll want to make sure that in the search from list that we have the correct library set up. We have drugs neutral masses. We'll be searching that for the empirical formula data. And we'll add a hydrogen to our neutral masses in order to search this particular spectrum. So we'll hit search here, and we'll find that we have search labels come up as metaxalone and secobarbital. Now the secobarbital may or may not be present, metaxalone may or may not be present, but we'll have to confirm from there what it possibly could be. But that would give us an idea on our screening that we have one or both of those particular drugs present. Now we can search for dimers, and we'll find that that 443 peak is in fact the metaxalone dimer, which kind of helps us to determine that that's probably what we have in this particular sample. Certainly it could be a mixture. Let's pull up search this against the libraries, the Virginia libraries, and once again I'll have to navigate to where those libraries are. Here they are. And we're going to search the preparation library at 20 volts, which will be this one here, and we'll search that. And say OK to that statement. All right. And what we get here are actually two different hits, the first of which is the metaxalone. Let me put that in mirror spectrum for us. And let me research that so that the mirror spectrum will come up. And there we can see that the metaxalone at 20 volts matches that particular saved spectrum. The top blue spectrum is our unknown spectrum, and the bottom red spectrum is our library hit. Now what we'll want to see is we also think that there may be secobarbital present based on the empirical formula search we did first. So we'll look at that, and we'll notice that the peak that it labeled as secobarbital probably is not secobarbital, since secobarbital will give a large 239, and certainly this 169 does not show up at all in this particular spectrum. So I think we can feel pretty good that the metaxalone is probably our best guess here for what we've got. Now we'll check that by going to the 60 volt data, and let's go ahead and look at that. Once again, I've got to make sure that we've got the right data here. Which this does not appear to be the right data. Let me go back and make sure we've saved the correct data here. I know it's supposed to look like this. Replace that. And that is not what I'm expecting it to be. Despite the fact that I've navigated to the correct location here. Alright. Actually, let me close search from list and I'll reopen it. That's still not the correct one. This not being my instrument here. Try to replace that one more time. That one it opens correctly, and that one it does not. Try this one more time. Alright, we finally have the correct spectrum up here. Alright, so now we've pulled this up. This is the 60 volt spectrum that we saved in the spectrum viewer. And what we'll want to do here is not search the drug's neutral masses, because at this point we've probably, there's a possibility that we could have lost our molecular ion. In this case I'm not sure we have, but we'll go here and we'll search the library spectrum one more time, and we're going to search the 60 volt preparation library. And we'll see what we get for a hit here. And we'll find our top hit is metaxalone. And once again, let me pull up the mirror spectrum so you can see that. And just research it real quick here to show you that I think you'll see very nicely that the metaxalone spectrum that we created today matches very nicely with the metaxalone spectrum that was in the library from the Scalaxin tablet. Alright, and that is, I believe, the end of my presentation for today.